So Chapter 6, Section 6 is really similar to what we did back in Chapter 2. In fact, we are just going to be introducing two new parent functions, and this section is really just all the shifts, so vertical, horizontal, reflections, and translations. So the same stuff that we've been doing in all of the sections, but now we're just going to apply it directly to trigonometric functions. The horizontal stretching and shrinking actually makes a lot more sense with these ones, as we'll see as we do some of those examples. So let's go ahead and start with example number 1. And example number 1 behaves exactly as you would expect. So before we dig into example 1, it says transformations of the graph of sine and cosine. Our goal is to graph functions of the form y equals a times sine bx plus c plus d, and similar for cosine. Both of these are of the form, and this is where the stuff from chapter 2 comes in, y equals a number times f composed with something plus something else. So the first thing we want to talk about is vertical transformations. So they behave in exactly the way that we think they should, and what I mean by that is, if we started with our parent function y equals sine x here, if we do y equals sine x plus 2, it just takes that graph and shifts all of its points up 2 units. Similarly, if we do y equals sine x minus 3, it just takes our graph and shifts all of our points down exactly 3 units. So this is the same rule that we were using back in chapter 2. So adding or subtracting a number after our trigonometric function, like we saw here, takes and shifts our graph either up or down that many units. So then, if I had the function y equals sine of x plus 4, that would take my graph, and this is my d value, so that's going to move it up 4 units. So I would have my same function, so I'd start with my parent, and then I just move everything up 4 units. That's not terrible, but that's the general idea. So that would be the graph of the sine of x plus 4. So the next one, which is also familiar to us, is vertical stretching and shrinking. So once again, if we start with our parent function this time, and this graph is a little busier, we have our black function right here is our function y equals sine x. So the vertical stretching and shrinking has to do with the same thing. If we multiply by a number bigger than 1, it's going to stretch the graph. So if we look at our graph in blue right here, we have multiplication by 4. And that took our graph and stretched its y values, which its biggest y value is 1, and stretched it all the way out here to 4. And its smallest y value all the way down here to negative 4. We also have, if we look at this one right here, we have 3, but this time it's negative. So when we have a negative, not only does that stretch the graph by a factor of 3, but the negative sign also reflects. So we'll notice here on our black graph, our max was at positive 1, but now, instead of being a max, it got reflected across the x-axis and it ended up down here at negative 3. And similarly here, it was at negative 1, it got reflected to positive 1 and then stretched by a factor of 3. So, looking at our very last one, we have our graph in green down here, 1/2, does the same thing, but instead of making the graph larger and stretching it, since 1/2 is less than 1 in absolute value, it shrinks the graph by a factor of 1/2. So notice the conclusion is the same conclusion that we had back in chapter 2. So the coefficient A tells us about the vertical stretching and reflection. But now in terms of these periodic functions, the coefficient A is also the amplitude of the wave if A is bigger than 0. If A is less than 0, the absolute value of A is the amplitude of the graph, and it's reflected across the x-axis. So if we were to check that, let's go look at our graph right here, y equals negative 3 sine x. Well, its maximum value is positive 3. And its min is negative 3. And the amplitude, remember, was 1/2 y max minus y min, which is 1/2 times the absolute value of 6, which is indeed 3, which is the same as the absolute value of negative 3 is equal to 3. So the coefficient in front of the trigonometric function tells us its amplitude. Well, the absolute value of it does. If it's negative, we take the absolute value to get the amplitude, but then we know the graph has been reflected across the x-axis. All right, so now it's your turn. Let's have you go ahead and you try number 1. If we identify our A in this case is going to be negative 6. So then the absolute value of A is the absolute value of negative 6, which gives us 6. So the amplitude of that wave is going to be positive 6. Alright, so let's go ahead and take a look at example number 3. First thing we need to take note of is that I have a typo. So it starts off with vertical stretching, but this should really say horizontal stretching. So we just did vertical stretching, that's the amplitude. So this one is horizontal stretching. So example 3, horizontal stretching, shrinking, and reflections across the y-axis. So our parent function in this case is once again is just y equals sine x. And that's our black wave that we have going on here. And if we replace x with negative x, well, that's the definition of it being an odd function. If we get the same thing, or definition of being an even function, if we get the same thing, and getting the negative would make it an odd function. So if we look at our red wave, we'll notice that there's more than one way to think about this. If you were to take the black function and reflect it over the y-axis, that would mean that this point would get reflected to here, And it would mean that this point would get reflected to here, which both of them would land exactly on the red function. So horizontal reflections occur when the input is negated. The period of the wave, which is, remember, the period is the smallest value where the graph starts repeating itself, or the frequency of the wave changes when we alter the coefficient. So this is function composition, and remember how back in chapter 2, whenever we had function composition, things seemed to not behave quite the way we would expect them. So if I look at sine of 1/4 x, I'm taking 1/4 of x, but then if I look at my green graph, on this entire graph, I don't even get through one period of this entire thing. It took and stretched that wave horizontally and made it very, very long. Similarly, if I look at y equals sine 3x, between 0 and 2 pi, that was its original period. Well, how many times did this go up and down again? So there's 1 copy, 2 copies, and 3 copies between 0 and 2 pi. So both of these observations suggest the following. The period of a wave is given by 2 pi divided by b in absolute value. If b is less than 0, the graph reflects across the x-axis. So if I come up back to our first one that we talked about, our b value would be 1/4. So then our period would be 2 pi divided by 1/4 in absolute value. So we can make 2 pi into a fraction by putting it over 1, and then we multiply by the reciprocal, which is 4/1. So that would tell us the period of that function, or it doesn't repeat, or it only repeats every 8 pi units. And that's why when we looked at our green graph up here, we noticed it never actually got back to where it started. It would need to keep going. And that's because our graph isn't 8 pi units wide. It actually only goes from negative 3 pi to positive 3 pi. So that's 6 pi units. If we take a look at this one, we see our b value is 3. So using our same formula, 2 pi divided by b gives us our period, which is just 2 pi over 3, which means that this is going to complete one cycle in 2 pi over 3 units, which is exactly what happened if we look at a trace of our graph. Went up, came back down, and it started repeating itself after 2 pi over 3. And then at 4 pi over 3, it had done it again. And then finally at 6 pi over 3, which is 2 pi, it had made 3 full copies of itself. So the horizontal stretching and shrinking depends on the coefficient in front of the x. The formula that we're going to use to find the period is 2 pi divided by b in absolute value, where b is the coefficient on the x value. All right, it's now your turn. All right, so to find the period of this, the first thing we need to do is identify our b. So our b value is going to be 2 pi over 3. And then our formula for the period was the absolute value of 2 pi divided by b. So in our case, this is going to be 2 pi divided by 2/3. So if we have a fraction divided by a fraction, we multiply by the reciprocal. So 2 pi over 1 times 3 over 2. Our 2's reduce out And we get that the period is going to be the absolute value of 3 pi, which is just going to be positive 3 pi. So the period of sine 2 pi over 3x is going to be 3 pi. All right, let's take a look at our next one. So I want you to contemplate the following question for a second. So how are the graphs of f of x equals sine x and g of x equals x minus 2 pi related? Well, what is the x minus 2 pi going to do to g of x? So g of x is f of x shifted right 2 pi units. Okay, so it's the same graph shifted 2 pi units right, but we also know the period of sine x is 2 pi. So that means that f of x is equal to f of x plus 2 pi for every value of x. So if we shift a graph 2 pi units to the right, what's going to happen? So the graphs are the same because sine is 2 pi periodic. Let's grab our graphing device and take a look at that. So if we were to clear out both of these, and if we grab sine x, and then we graph sine of x minus 2 pi, and I'm going to go, zoom and choose choice number 6 to go back to my standard window. It first draws sine x, and then it's going to draw sine of x minus 2 pi, and we get exactly the same graph. And if I go second table, I will notice that my outputs y1 and y2 are exactly the same for all of these. So the graph of sine x and the graph of sine of x minus pi over 2 are exactly the same graph. All right. So now, before we talk more about horizontal shifting, there is a warning that we need to take heed of. So if our graph has both a horizontal stretch or shrink and a horizontal translation, we have to do some algebra before we can identify our shifts and stretches. So when both b and c are present, we must factor out b before calculating the horizontal shift. So what that says is if I have sine of bx minus c, I need to factor that into the sine of b times x minus c over b, and this is going to be my horizontal shift. So in essence, before we can calculate the horizontal shift, the coefficient on the x needs to be 1. So we're going to have to do a little bit of algebra before we can do that. And then the b is still the same as it was, which is our horizontal stretch and shrink. I'm missing an R in there. Shrink. All right. So let's go ahead and do an example to illustrate. So find the horizontal translation and the period of this. So according to our warning, we have exactly this form. We have our bx minus c. So before we can calculate this, we need to factor this into that form. So my b value is going to be 2, so I need to factor a 2 out of each of these. That's going to be sine, and I have my 2 and my x, but now the pi doesn't have a 2. But if I want, I can always write any number as a fraction by putting it over 1. And then if I wanted to, I can build that fraction by multiplying the top and the bottom by the same thing. So it's worth noting, pi is the same as 2 pi over 2. And if I have that this is the same as 2 pi over 2, if I factor this 2 out, then what's going to be left behind is the pi over 2. So we can factor out a coefficient that isn't there by building a fraction as needed to create the coefficient that we want. So now we can use this to find the horizontal translation is going to be this. So it's going to shift right pi over 2 units. Then we have our 2, our coefficient of 2 is going to change our period. And from the previous section, or the previous example, we have that the period was 2 pi divided by our b value. And we have our b is 2, so that's going to be 2 pi over 2. The 2's reduce out, so the period of this is going to be pi. So our graph will be shifted to the right, pi over 2 units, and the period is going to be pi. All right, well, let's go ahead and do this U-try. So we identify our b as -4, and if we factor that out, we're going to have f of x equals -3 times the cosine of -4 times x minus pi over 4. So then we have our a value, it's going to be this. So we have our a is equal to -3. We have our b is equal to -4. And then lastly, our horizontal shift, so our c over b is going to be this. Let's not use that color. Let's use this one. So then the amplitude is the absolute value of -3 is 3, and then we're going to reflect across the x-axis. That's what our A tells us. B gives us our period. So we're going to have 2 pi over negative 4, which is going to be pi over 2. And then this one is going to reflect across the y-axis because it's negative. And then finally, our horizontal shift is we are going to go right pi over 4 units. So we can combine all of these different things together to get our shifts for that graph. So it's going to have amplitude 3, reflect across the x-axis. Its period is going to shrink to pi over 2, and it will be reflected across the y-axis. And then it's going to have a horizontal shift right of pi over 4 units. And that's going to be everything that we need to know about